Let's define a couple of matrices. The first one is going to be R, and it is the ratings matrix. It's the matrix that contains all of the ratings. We would see it here. And it has dimensions of M by U. And M we're going to use because it designates the movies. And U we're going to use because that designates the users. We have another matrix called P, and P has dimensions of M by K, and K is going to be our features. And we have Q is another matrix whose dimensions are U by K. And so if we want to see that pictorially, it's down here at the bottom. We have the R matrix, which is filled with ratings from 1 to 5. And we have a couple of spots where we have a question mark and we don't know what the user would rate for that, and that's where we would want to make a prediction. You could see here that one of the dimensions is M, and these represent the movies, 0, 1, 2, 3. And then we have U at the top, and that would represent the users, right? User 0, 1, and 2. And now we have this other matrix over here, P, and we could see here that the dimensions are M by K. K would be the features. Notice here that M has the same number of rows as M in the column R, and then we have Q, which is a matrix of U by K. Right? Okay, so those are the matrices that we're going to be working with. What we're trying to do is take this matrix and reduce its dimensionality by factorizing the matrix and coming up with a P and a Q. The problem here is, how do you come up with a P and a Q? So we're over here, and we have R is going to be approximated by the matrix P, cross product by Q transposed, right? So here we have Q transposed would rotate it 90 degrees clockwise, right? So we got U at the top, and we have K on the left side, and that's what we have here, right? So we have this matrix here is approached, or it's approximated by the cross product of P times Q transposed, right? Notice here that we have movies and we have users up at the top, and the cross product, if you don't remember, is row times column. So we do that times that plus that times that, and that would be our the first element, or the top leftmost element on the resulting matrix. And then we would do the same thing with these two, where we would do that times that plus that times that, and that would be the top row middle entry on the resulting matrix, right? That is going to be approaching R. Okay, so that's what we have. And then we have the matrix factorization using matrix reduction via gradient descent. So R hat would be, let's assume that is the matrix that is the result of multiplying P and Q, that is approximating R, right? And so what we can say is R of MU, and that would be an n element in the resulting matrix, right, is equal to P M times Q K transposed, right? And so PM, if you look here, would be this entire row, right? Cross product with QU, which would be this entire row. Yeah, I'm sorry, that's wrong right here. This should be a U right here, right? U transposed, right? So these are two rows in the in the matrices P and Q. So if we can write it a different way, we would write it using a summation. Right. So we got n is equal to 1 up to n, and that is the number of columns, or I'm sorry, the number of entries. And what we're going to do is we're going to multiply P of mk times Q of uk. So what that describes is the process of multiplying the row times the column, right, and adding them all up. So yeah, that's that. And then since we have that, right, so this is going to be the element in the matrix. Now what we want to do is we want to figure out the error function for that calculation. Okay, how much does that result differ from the actual matrix, right? So let's say we run this, which is going to be this row times this row, right? And we come up with the number 4. Now we want to figure out how much of an error do we have. And how do we figure that out? Well, we take the entry in the matrix that we're trying to approximate, and we subtract that number, right? So that's what this here is, right? So the error of mu is equal to r mu, which is this value, minus r hat mu, which we defined up here as being the row times the column. So it's basically that minus that, right? And then, yeah, another way to write that is r of mu is equal to r hat mu. I'm sorry, r of mu minus r hat of mu, and r hat of mu is the summation of the row times column, and that's what this summation here is speaking on. And then what we can figure out is sometimes this is going to be bigger than that number, sometimes this value here is going to be smaller than that number. So sometimes the result of this equation is going to be positive, sometimes it's going to be negative. So what we need to do is we need to take the square of it, right, so that we can ignore the fact that it's less than or greater than, right? So we'll square it, and we get this value here, right, which is can be expressed as this value here, right? And yeah, so that's our error function. Okay, this is our error function. So now if you remember from gradient descent, using linear regression, what we're going to do is we're going to take the derivative of the error function, and that is going to tell us how much we need to push our p and how much we need to push our q values in which direction, in a positive direction or a negative direction. Right? So that we can get to the minimum, so that we can get to the place where it minimizes the amount of error, right? Because we're trying to approximate a matrix R hat that approximates R, right, and minimizes the amount of error. So it's not going to be perfect, but it's going to minimize the amount of error. It's going to be like 3.1, it's going to be 4.85, it's going to be 0.8, right? It's going to be close, but it's not going to be exact. So that's our error function, and then we're going to take the derivative of this, right? So here we're taking the derivative with respect to a specific element in the P or matrix, right? PMK. So we're taking the derivative with respect to this one value. Right? And when you take the partial derivative with respect to P of MK, what you're saying is you're saying that P of MK is going to be the variable. That's the thing that we do not know. Okay, and we're taking it with respect to P of MK on E mu squared, which is this equation here. And so to take the derivative, we use the chain rule. We're going to pull the 2 down. We are going to subtract 1 from the exponent, so that's going to turn to 1, which is going to make it go away. And then inside of our parentheses, we're going to have this expression, right, which is the same as this expression here. This expression, but using the chain rule, we need to multiply by the derivative of this expression here inside of the parentheses, right? And so the derivative of what's inside of the parentheses is this value here. R of mu is a constant. It is a number 3, right? So that will go away when we take the derivative. And then minus the summation of this expression, right? And if you look, you'll see that when you take the derivative of a summation, what you're doing is you're taking the derivative of every single one of those steps in the summation. Okay, so P of MK times Q of UK, and we're going to do that repeatedly as K increments. Okay, so what you can see here is that Q, right here, Q, the Q value is going to be a constant, right? And the P of MK is also going to be the variable, okay? Because we are doing the partial derivative with respect to P of MK. So what you get over here is the P of MK turning into a 1 because it is the variable. It's like an X. And then the Q of UK is the coefficient, so that remains, and the Q of UK is negative, right, which gets pulled out over here to the negative 2. Okay, so this originally was a positive 2 when we pulled down the 2, but it becomes negative via the negative QUK, which is the coefficient of this variable, which is one element in the summation. Right? This summation has a bunch of elements. Right? In this example here, it has 1 and it has 2. Right? But what we're doing is we're not taking the partial derivative with respect to this value and that value. These two are not both the variable in the equation. What is the variable is this one value, right? So that means this guy over here is a constant. This is a constant, that's a constant, right? So this summation over here, the only element in the summation that has a variable is the one involving P of mk. So that's the only one that remains. The rest of the elements in the summation are 0 because they're constants. And then when we take the derivative of this, what we get is negative QUK, because the P of mk is the variable and its coefficient is Q of UK. We get that negative QUK, pull out the negative sign, and we get this equation here. Right? And then we kind of replace this value here with E of mu, which we can see is equal up 2 steps above, and we get this pretty little equation, right? But what is this equation? It is this here, right? And what is this r hat of mu? It is the summation. It's the row times column. It's right here. Okay. So this is going to be our derivative, partial derivative with respect to p of the error function. Okay. So now this is going to tell us whether we need to push up or push down. All right. And so I'm sorry, I think I skipped a step, but right here we're also going to take the partial derivative with respect to Q of UK. Right? And if we do that, you can kind of work it out that it's going to come out with the exact same result, except this here is going to be P of MK. Okay. So what we come up with is that the new value for P of MK, right? The new value of P of MK, this one, let's say that this is the one that we were trying to estimate, is going to be the original value of P of MK plus the error, right? Plus the error, the partial derivative of the error function with the sign flipped, right? Because if the error function, like remember in linear regression, if the error function was this way, right, we didn't want to go that way. We wanted to go down, right? We want to go down to the minimum. So to go to the minimum, you don't want to follow the derivative upward. You want to take it downward by flipping it to become positive, right? If it was positive, we would flip it to be negative. If it's negative, we want to flip it to be positive. And that's what we want to do right here, and that's what we're doing, and that's going to be our new value for P of MK. Right? And we're going to do that as we iterate through the P matrix and we iterate through the Q matrix. This is what we're going to be following, right? But there's a problem with this, right? So the problem here is that let's see. Let's say we start out with P and Q, right? If you remember from linear regression, what we did is we picked any line, and then we iterated through the process, pushing the lines, M and B, nudging it until we finally got the approximation, right? After 5,000 iterations. That's what's going to be happening here. Okay, we start with 2 matrices, and we can fill it with any values, right? Negative 1,000, negative 1,000,000, in all of them, and that's going to be our starting place. So since our ratings here are 1 to 5, I guess a good starting point would be 2.5, right? So if we filled all of these values with 2.5 and we use that as a starting place, I guess that would minimize the number of iterations, or it might be it just makes sense to start at 2.5. So if we run through this, let's go ahead and run through this, right? What we're trying to find out is what's the new value for P of MK. What's the new value of this after nudging it in the right direction to minimize the error, right? Well, we take the original P of MK, which is going to be 2.5, and we're going to add this expression to it. And remember, the 2 So let's say plus 2 times E of mu, and E of mu is this expression here, and this expression is going to be the summation of the row times column. Right? So what it is let's take this example here actually, right? Let's pretend these are all filled with 2.5. So what we're doing is we're taking R of mu, which is this 3, right, times, whoa, let's see. So here we have 2 times E of mu, and E of mu is equal to this expression here. So it's going to be R mu minus R hat of mu. And
the United States of America, and to the republic
for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Don't forget that the door decorating contest ends today. Also, there will be hot chocolate with link room during lunch. Thank you and have a great night and day.
All right, so E of mu is equal to this expression, and then we're going to multiply that by Q of uk, right? And so what is R of mu? Well, R mu is the original value, right? So we're going to take 3, and we're going to subtract R hat of mu, right? And so R hat of mu is the row times column of the two P and Q matrices, right? So we're over here, and let's say we start out with 2.5 on every one, and so these are the row and column that are relevant to our like process here. And so what are we going to do? We're going to do that times that plus that times that, and the answer that we get is 6.25 plus 6.25. Yeah, so 2.5 times 2.5 is 6.25. So it's 6.25 plus 6.25. So we're going to get 12.5, right? And then we're going to multiply by Q of uk. Q of uk is going to be 2.5. Right. So let's work out the math and see what we get. We get 2.5 plus 2 times, what is this going to be? It's going to be 9.5 times 2.5. Okay. So if we can estimate, and we'll call this 10, we'll call this 2, and let's multiply it all out. We get 4 times 10 is 40, so we get 42.5 as our answer. Okay. For what P hat of mk should be. I'm sorry, not P hat, but the new value of P should be 42.5, right? So we're going to replace that with 42.5. Now that's ridiculous, right? So what we need to do is we want this expression here not to be some huge number. We want it to be telling us whether we need to nudge the original P value up or down. We wanted to nudge it, right, in a regressive way. So we want to nudge it up like 0.02 or nudge it down 0.02. So what we're going to do is introduce a learning rate right here. So this guy here would be the learning rate. We're going to set that equal to 0.002, and that will cause this number to be a fractional number, and we are going to push P upward on this iteration, and then we're going to reiterate the whole way through until we so then we do that for P, and then we're going to do the same thing for Q of uk, and then we're going to move on to the next value in the P matrix, which would be P of 0, K of K1, and do the same thing. Right? And this can do it again and again and again and again and again and again, and then what you're going to see is that these 2.5s are all going to be pushed over to these values that we're trying to approximate via stochastic gradient descent. So hopefully that was clear. I know there was a lot of inaccuracies in the explanation, but that's generally how it's going to go.